Zach Sample, Technical Support Engineer here at XP Software. And today we'll be going over a conversion of a HEC-RAS model into XP, as well as the benefits of utilizing 1D, 2D modeling. So to get in a little more detail, we'll be discussing 1D model conversion basics, HEC-RAS and XP 1D differences, HEC-RAS conversion walkthrough, as well as a short XPSWM 1D model demonstration. And once we get into the second half of our presentation, the integrated 1D, 2D hydraulics modeling, we'll talk about 1D hydraulic model limitations and 1D modeling issues, 2D hydraulic modeling overview, as well as an integrated 1D, 2D model example. So to begin, there are a few expectations and limitations that should be kept in mind when doing 1D modeling. First and foremost, two different models will never produce the same exact results. Now this is probably the most important thing to keep in mind, as even if you had the same version, the same model, and you changed minor cross-section geometry or changed the time step used, you would still produce different results. Now, as you can probably see, that if you were to convert different software packages which solve different calculations and have different run engines, these will never produce the exact same results, though, as I'll talk about shortly, can be calibrated to have approximately the same results. So one more thing, the new model data will only be as precise as the previous base model data. So if you have a model which has inappropriate model cross-sections, inappropriate model data, this will be translated into the new model and will then be just as inappropriate. So as I said before, all physically based models can be calibrated to record a data. And if gauge data is not available, things such as a rational calc flow can also be used to calibrate models. And so the differences between HEC-RAS and XP1D. HEC-RAS model, there's a steady and unsteady model. These solve primarily the momentum, energy, and continuity equations. The HEC-RAS model is a cross-section and relative downstream distance model configuration. Also, the HEC-RAS model is purely a 1D hydraulics model. XP, and when I refer to XP, I'm referring to XPSWM and XPSTORM. XP is a fully dynamic 1D model. Now, it solves a dynamic wave routing solution and solves the complete St. Venance equation, which produces the most theoretically accurate results. This takes into account complicated flow, gravity flow, pressure flow, flow splits, backwater effects, these such things. Now, a XP model is based on link and node model configuration, which we'll see in a little bit later on in the presentation. Now, XP modeling includes 1D and 2D hydraulic, 1D sanitary, and water quality modeling options. The actual conversion of a HEC-RAS model will be in a few steps. The first is importing the reach center line into XP. The second would be then to split that center line into appropriate XP links and nodes. Now, it's important to note that every link in XP represents a single cross-section. From here, we would then import the HEC-RAS cross-section geometry, input vertical information such as the inverts and spill crests, input the inflow hydrographs from a HEC-RAS model, as well as recreate any structured or closed conduits that are used. An XP model will automatically convert the HEC-RAS cross-section geometry into XP. Now, a more manual conversion or importing will be required to bring in the reach center line and section lengths, the inflow hydrographs, as well as the structure and closed conduit information that's used in HEC-RAS. So the first step of the importing the reach center line, this data is contained in the HEC-RAS G0 file, and this file contains not only the reach center line but also the cross-section information. Now within XP, you will create a single link and assign the upstream and downstream node coordinates of that link to the upstream and downstream reach coordinates of the HEC-RAS reach. From here, the reach coordinates from the center line of the G0 HEC-RAS geometry file can be converted into an XPX file format, which is a text file, with a format shown below. So effectively, you have a text file, which would have vertex start and then the link name, and then you would have the vertices listed, and then vertex end. And you can convert this XPX text file directly into an XP model using the import export data, import XPX data, and this will automatically update the center line reach that you've created in XP with the vertices. From here, we can use the calculate conduit length option in XP, which will automatically then associate lengths to that reach. So next, now that we have our reach drawn in XP, we can split the reach into the appropriate links based on the HEC-RAS cross sections. You can split a conduit or a link in XP by right-clicking on the link and selecting Split Conduit. Now this is obviously very helpful in this scenario. Also, if you have an existing XP model, and let's say you needed to add a manhole or a junction, you can split the existing link, which will use the Split Conduit dialog, as you can see on the right. And in our dialog that we have shown here, we have just over 9,000 foot length of reach, and you can split that in any number of length increments. And when you do so, it will automatically update the slopes, invert, spill crest elevations of the two conduits you've made. So now that we have split the reach into the appropriate sections, we can import our HEC-RAS cross-section data into the XP global database. Using the file import export data, import HEC-RAS data in XP, we can select the appropriate G0 HEC-RAS section file, and then the next import step would be to associate the shapes, the HEC-RAS shapes, with the corresponding XP link names. Again, I'd like to note that in XP, one cross-section per one link. And so now that we have the cross-section shapes and the actual river reach itself, we will need to input the vertical information. Now, there's two general methods to input vertical information into XP. One, in this case, would be a manual approach. You can manually reference the relative cross-sections and then input the lowest cross-sectional point as the invert value of the link or conduit. Also, if you have a number of these points to input, you could create an XPX formatted file, which, as we saw before, can directly be imported and will update the appropriate model objects. The second method would be to update the inverts automatically using a tin. Now, we'll see this a couple times later on in this presentation, but you can automatically set node and link inverts using a tin with the XP modify options. Now, this includes setting the invert or the ground elevation from a tin at any node, as well as setting the node inverts, the node inverts to the lowest connected link inverts. From here, since we have, at this point, we will have a river reach with appropriate vertical information as well as cross-section information. We can import our inflow hydrographs from HEC-RAS. This is a simple copy and paste procedure. You can just copy the hydrograph table from HEC-RAS into any given node in XP using the user inflow option. Lastly would be a conversion of any structures or roadway crossings in HEC-RAS. So as you can see in the lower right is a typical representation of a HEC-RAS crossing. So in XP, you can model the underpass of a crossing as a single natural channel shape, or if there are multiple flow areas by the use of piers under the bridge, you can use multiple flow area channel shapes in XP. Also, a maximum channel depth can be input to allow for pressure flow when the water surface level meets the bridge deck level. The overpass, the bridge deck itself, can be represented a number of ways, either as a rectangular weir, user-defined weir, or natural channel shape, which can account for the varying flow depths and deck profiles. Now, as you can see, this entire crossing can be represented as a single multi-link in XP. As you can see from this dialog example, we have a number of openings. We have 5 different openings, as well as a deck. The openings can be not only natural channels, but also conduits, closed conduits. And in this example, I have represented the deck level with a natural channel shape, as you can see there, that will take into account those varying flow depths as the flow would cross that bridge deck. And so that sums up our conversion of a HEC-RAS model into XP. Now, if you were to recreate a HEC-RAS model from scratch, or create a river model from scratch, a new project, you could do this in XP in 3 basic steps. First would be drawing the links and nodes. The second would be using the tools calculate conduit options to not only automatically drape and allocate the cross-section shapes to the given links, but also to specify or automatically input the link lengths. And then the third step would be to use the modify elevations option to set the inverts from 10 and offset the spill crest. Now I have a little demonstration here we can take a look at. And so I have a XP model, which I've already imported a background image and a tin. And I will show a drape of the tin so we can see that it does have a well-defined channel profile. As I had said before, we can start the model by drawing our links. Now you can either draw straight links, or holding the control button, we can draw links with vertices. As you can see here, I drew a short river reach. And now, using the tools, calculate conduit cross sections, this option, so I'm going to use for all links, and we can have the cross sections draped automatically, a percentage from either node. I'm going to have it be in the middle, so 50% from the upstream node. And I believe the river is about 50 feet wide, and so we're going to have the left bank be roughly 30 feet, right bank be 20 feet. So you can see here it automatically allocates those shapes, and these shape markers show where that was draped, and these red and black nodes indicate the right and left bank used. From here, again, the calculate conduit option, calculate lengths, so if I select all the objects, we can use modify elevations and set the inverts from the 10. So you can see here there's invert at each of the nodes and at the links. We can also generate ground elevations from the 10. So now our ground elevation is set at the same level that the invert is, so we can offset our ground elevation. And the river bed is about 20 feet deep, so we can offset that 20 feet. And so from here we could run our model. There's a few things which I previously had set up this node to have the inflow hydrograph. As you can see here, I have my inflow hydrograph, the upstream extent, and at the tail of the model I have an outfall. There's a number of outfalls you can use in XP. I've used a normal depth for this demonstration, free outfall. Now if you wanted to change, say, a single link section, you could come in here and delete the cross-section we had previously made using that automatic tool, and we can define cross-section layout manually. And so if we were to come in and say that's a more appropriate cross-section for what we've seen, so we can accept that, and within the link go into the natural channel and edit the natural channel shape, and we can automatically select the left bank and right bank points, as well as input the different channel overbank and channel center roughnesses. So from here we can run our model. And ultimately we can review the results. As you'll see here, as I play this simulation, you'll see that the cross-sections are inundated to an extent where vertical walls are being assumed. I will later on in the presentation discuss how this is an inappropriate assumption in trying to accurately model, especially river inundation extents. If in 1D a cross-section is not fully physically represented, it can provide erroneous or inappropriate results. So from here we will jump back to the presentation. Now that we've seen the conversion of a HEC-RAS model into XP, we can take a step back and look at 1D modeling in general. So 1D modeling is typically done to model the 1D hydraulics of pipes, rivers, and streets. This is done through a number of different programs. HEC-RAS, XPSWM, EPA-SWM, Mike 11. These are some of the many programs that can do this type of modeling. As such, 1D hydraulic modeling is the most common and well-known option in the U.S. for hydraulic models. And the models can very well model the flow that is contained within closed conduits and defined open channels. And so the limitations of 1D models, I guess, starting with that point, is that it is a requirement that you predefine the flow path in a 1D model. In essence, you must know where the water is going to go prior to model setup. Now, in a urban setting with a storm network, this is fairly straightforward, but if you get into open channel flooding, river flooding, often the flow paths are unknown, and so this can cause quite a bit of time to be spent making assumptions and attempting to model the appropriate volume storage and flow paths, which ultimately still may not be done appropriately. Again, the water must be contained, even if you have found or believe you have the correct flow path designated in 1D, the water still must be contained within our representation of the channels, pipes, or streets. A 1D model cannot accurately represent the existence of complex 2D flow patterns, braided streams, for instance. 1D model is generally provides a poor description of the hydraulics of a broad floodplain flow, as well as is often quite difficult in creating accurate floodplain mapping. So here are a couple example slides that I had from a couple models that show these inappropriate cross-section areas. So for one, if you look at the lower left and upper right areas, if the main channel has not, I guess, overtopped yet, in this model, these areas would receive flow. And when the main channel does overtop, this area on the right is shown to be an active flow area, which is inappropriate. Also on the upper left, there's a vertical wall being assumed, which in this actual model, that vertical wall is inappropriate, and that flow would be spilling out into an adjacent community. So another example, on the left we have a place where the flow area was known to be inappropriate, so it was blocked out, but in 1D modeling you often don't know the extent of the water levels or the flow path until you run the model, and so that blocked out area was obviously not efficient. And on the right again is that same section which only at the very peak of the flood overtops. And the last slide here is of that. This is probably the clearest example of, we have flow area which is being calculated a little under a mile from our main channel, which wasn't shown to overtop. And so if we progress on to 2D modeling with XP2D, the XP2D module is a FEMA-approved add-on module for XPSWM and XPSTORM. The 2D models can much more accurately simulate the hydraulic flow in areas with unknown flow paths and flood storage areas. The computational engine of the XP2D is coupling of the XP1D engine and the 2-flow 2D unsteady flow models. 1D is calculated using the implicit Gauss-Seidel under-relaxation methodology, and the 2D 2-flow engine uses the implicit Stelling ADI alternating direction scheme. 2-flow itself is a commercially available 2D hydraulics program developed by WBM and the University of Queensland in Australia. Now, the important thing with XP2D is the 1D and 2D solutions are solved simultaneously, which means the water level and flow can be shared at nodes and grid points, grid cells. So if we think how this could be utilized for a integrated 1D 2D system, a 1D 2D coupled model will use the best description of the flow for each hydraulic area. So the 1D dynamic flow calculations will be used to simulate flow in closed conduits, pipes, culverts, as well as clearly defined channels. The 2D flow modeling will be used for the rest of the simulation, all of the overland flow, surface flow, and floodplain flow. 1D inlets, channel banks, and manholes can all be linked to a 2D cell to share and transfer water levels and flow. Now, the types of 1D 2D linking, so if you see here our example of, we have our 2D grid with our 1D channel going through the middle. The 1D channel area is blocked out in the 2D grid, so as to not provide a doubling of storage area. If we have our 1D channel blocked out, we can have our underground closed conduit network connected at nodes, but those cells do not need to be blocked out, as you'll see in the next slide. So our closed conduit underground network can be connected to the grid at nodes, and so you can see the way the flow can travel between the two systems. The flow can either surcharge from the 1D network out onto the 2D grid. Alternatively, it could originate on the 2D grid, and the flow can either originate on the 2D grid and then enter back into the closed conduit network, or a 2D inlet restriction can be applied, which can only allow a given amount of flow back into the closed conduit network, and the rest will be passed along the 2D grid. So if we get into an example of how you can set up a 1D 2D integrated network, first we begin with our example here. We have a 1D open channel basic network. The main reach you see is our open channel, and the lower portion of our 1D network is a closed conduit urban network. So if we apply a tin to this, we can, as you can see here, our tin, we draped this section here to show that we do have that clearly defined flow area for our 1D model to assess. once you have a tin and this existing 1D model, you can set up your 2D grid. Essentially, you would drape your floodplain area with the grid. And at this point, you can set up any nodes. You can connect the nodes. Any nodes you would like to share flow, have them be shared between the 1D and 2D networks. You can, at these nodes, select link spill crest to 2D or link invert to 2D, whichever is more appropriate. From here, you can block out, as we mentioned, block out that 1D channel so there's no doubling of flood storage area. And once this is blocked out, we can add our active floodplain area, which is shown in that light pink orange color. And then the light blue is our 1D 2D interface line. So that is what is connecting the interface between the 1D network and the 2D active grid. Another feature is we can add any number of different plan use roughness areas to our map. So you can see here we have our different floodplain roughnesses, our urban roadway. And once all of this is set up, effectively you can run your model. That's really all that it takes for input. And so once you run the model, you can see here that we have our 2D results. Now the 2D results are automatically generated in a 2D map. So we have a number of maps which we can display. We can look at not only water depth and water elevation, but also flow and velocity vectors, as well as a hazard map and fluid number map. And so if we were to set up our results to display a water depth map, we can see that the zero depth, the edge of our depth map, is our floodplain boundary. Alternatively, we could set up a water elevation map, which would allow us to report BFE lines, and we can set up our contours at any given interval. I believe this is set up at 1 foot increments. Another feature of XP, in this case XPSWM, is we can not only show these different water depths, water surface elevations, velocity vectors, we can also export those to an Esri grid. We can export them in the actual cell elevations, so we could export the depths as a cell block. We can also export contours made from these, so we could set up our depth or elevation map and export those contours themselves. Now so that XP demonstration, which we had earlier, I have set up a similar model, which I linked to 2D. As we've talked about, I thought it might be fun to see what it would look like in an integrated system. So, as you can see, we have our 1D network in the model with our floodplain area blocked out. So there's no doubling of storage. Now, from here, we can see that I have added these 1D, 2D interface lines, which I'll turn the grid, and so we can see that those interface lines will transfer flow to those grid cells. And so if I turn this off so we can best see it, the model will begin. We can review the simulation. I have the depth, water depth being shown, and we can play the simulation. We can see the flow enter the model. Now, additionally, we can skip forward in the simulation to a given point. And if I turn on the 2D flow vectors, or sorry, the 2D velocity vectors, we can see the flow enter the system and ultimately spill out of the banks. So as you can see, this is something that which would be difficult to accurately model in just solely a 1D environment, especially the flow transfer at node 102 and across this bend junction here. And as I said before, these maps, these 2D results maps, can be exported to an Esri grid for use in external software. And so that concludes the presentation which I had set up to discuss the HEC-RAS model conversion and 1D, 2D modeling. Again, I'm the technical support engineer here at XP Software, and you can get a hold of me and the technical team here by emailing support@xpsoftware.com, as well as going onto our website, xpsoftware.com, and under the Expert Care section, we can or you can utilize our service requester and knowledge bank portion of our site. Thank you very much for watching the presentation, and model with confidence.